Hello, we are Team SkyPixel. We are excited to present our project, satellite imaging-based crop type mapping for small fields semantic segmentation. This project is a response to the pressing issue of chronic hunger in Africa, a continent where over 300 million people are engaged in agriculture, contribute to about 30% of Africa's GDP, and employing about 60% of the region's workforce. By leveraging advanced technology in agriculture, we aim to contribute to reducing food production shortages. In our presentation agenda, we will start by discussing the challenges presented by our problem settlements, then move on to the tasks we undertook, followed by the exciting results we've achieved. Finally, we walk through our approach and conclusion. We are addressing the critical issue, enhancing agriculture in Africa, a sector that employs a significant portion of the population and contributes substantially to the GDP. As the population grows and the hunger persists, the need for increased food production becomes more pressing. However, Africa faces unique challenges. Despite the crucial role of agriculture, there is a noticeable gap in the adoption of advanced technologies, particularly precision agriculture. Moreover, the prevalent practice of smallholder farming in Africa does not really lend itself to the application of state-of-the-art deep learning approaches. This has hindered many, such as aiming to contribute to the application of advanced technologies, such as satellite data in agriculture. We've employed the shifted Windows transformer unit architecture for our task. The dataset we trust consists of time series images from 3 satellites: Planet, Sentinel-1, and Sentinel-2, also from Ghana. Our dataset is split into 2,210 images, 208 validation images, and 909 test images, ensuring balanced presentation of classes in each set. These images are time series captured throughout 2016. Sentinel plays a pivotal role in our approach. This satellite carries a synthetic aperture data operating in the C-band, making it immune to cloud interference with motorized 3 channels: vertical polarization, horizontal polarization, and regulation. Sentinel-2 provides multispectral images with varying spatial resolutions: 10 meters for visible bands and nearly 20 meters for 6 bands, and 60 meters for 3 bands. For Planet satellite data, which boasts 3 meters spatial resolution and with this time of 2 to 3 days, we focus on visible bands, RGB, and infrared. Given our dataset time series nature during long periods, we approach it in 2 ways: randomly selecting an image in the time series dimension and averaging the time series throughout the long periods. Our method involves using data from 3 different satellites based on the promise that each crop has a unique spectral signature. We use the swing unit independently for each satellite and then combine the feature maps into convolutional layers to improve the accuracy of our crop mapping. We use various tuning techniques. We apply attention algorithm, and the success of our study hinges on 5 key steps: data fusion, leading the spectral values of each crop type, building a swing unit architecture for each satellite, combining the end heads of the 3 satellites, tuning parameters, meaning the number of layers at each stage. Our method uses the shifted Windows transformer, swing transformer, which hidden attention between pixels across entire images using the shifted Windows technique. The swing transformer, a key part of our process, works in 4 stages. Each stage partitions the image and passes it through the transformer block, along with the model to gather detailed information about the images. To improve the performance of the model, we used a fairly big swing transformer architecture with numbers where 2 to 18 and 2 for 4 stages respectively. The swing transformer is a neural network used for image segmentation. It is actually the swing transformer delivered as a unit architecture. For each satellite dataset, we employ an individual swing unit. These models are then unified by converting the spectral feature maps into a convolutional layer, which helps in outputting the feature maps. In the approach, the swing unit model architecture achieved a high accuracy of 93.6% using the swing unit model, which outperformed the related work that achieved 6.9% accuracy. The attention-based approach showcased promising potential analysis data for small fields. In conclusion, our approach focused on enhancing performance for small agricultural fields and achieve fairly general performance. The future works is to explore spectrums and also exploring the